wide awake. I know we are the last session of the day, so I will do my best to try and keep upbeat and keep you all engaged. I'm Dave Tucker. I'm a software engineer in the office of the CTO at Red Hat. I work in the Emerging Technologies Networking Group, and I'm here to talk to you about enabling next generation networking with eBPF. So we've got a fairly long agenda to go through, but basically I want to take you through what eBPF is, how it can be used, how we at Red Hat are already using it today, and then for those of you here for the networking piece, I'm going to cover why it's particularly good for networking. However, it doesn't come without challenges, and those are some of the things that we're trying to address today. So hopefully we can enable both Red Hat and our customers and partners to be successful with BPF in our platform. I'll give you a little bit of a demo, and then I'll open up for Q&A. So first of all, what is eBPF? Now, eBPF is probably one of the worst named technologies because it is not really descriptive of what it actually is. It has a legacy in packet filtering, but it is absolutely not what it is today. It is not a packet filter. It's basically a sandbox execution environment for kernel functions. So if anybody was watching Jim's talk earlier about WASI and WASM, it is really something like WASI or WASM, but for the Linux kernel itself. It allows us to extend the Linux kernel to change behavior, and it allows us to get unprecedented observability into what is happening inside the kernel, things that were particularly difficult to view before eBPF came along. Now, one of the very excellent properties of eBPF is that it has a safety mechanism. So eBPF programs are guaranteed to not panic the kernel or cause a crash. And they do so by employing a verifier, which will make sure that any BPF code that gets loaded into the kernel is safe and accesses safe areas of memory. And therefore, we can't end up in a situation where we cause a crash or a panic. Now, you can program the kernel in C, which is the de facto language for programming the kernel to begin with anyway, or you can program in Rust. And there is a data interchange mechanism for these kernel programs to talk to user space processes. So you may want to extend something in the kernel, or you may want to observe something in the kernel, but be able to respond to that data in user space or send it into an observability or tracing system. And that's where this programmability comes in. So ultimately, there are a couple of key concepts about eBPF. We have programs that allow us to extend the kernel. We have maps, which offer a data interchange mechanism from kernel space into user space. And we will be attaching these programs to hooks or trace points within the kernel. And those attachments are represented by a link, which is basically our reference to say there is a thing attached to this hook point in the kernel. So eBPF is slowly eating away at the core kernel functionality itself. Now, this is incredibly interesting because for our customers and our partners, some of the things that we've been wanting to do in the Linux kernel, like being able to upgrade or change the way that networking happens without actually taking the machine down or causing a reboot, are very difficult. But with eBPF, we can load a program in, which could be our network driver. We can then atomically replace that program, and then suddenly we've got the new version running without any kernel downtime needed at all. Now, kernel subsystem maintainers are starting to see the promise of this, and we're seeing the remote control. So everybody here has used a TV remote, right? We all still do that. It's not all smartphone based. So infrared is particularly annoying for the kernel because there are so many different ways of decoding infrared instructions. And the IR subsystem has adopted BPF as a way of modeling that. So they don't need to ship hundreds of thousands of infrared drivers. They can just ship little bits of BPF code that can be loaded in on demand to handle that. I came here from the Linux Plumbers Conference earlier this week, where Red Hat gave a presentation about extending the human interface device subsystem. So any USB keyboard or mouse or anything which plugs in and allows human input into a computer, those drivers can actually be better represented in BPF than having custom drivers in the kernel. So again, we can get a quicker update cycle when we need to send a patch or a new device appears. So if I were to predict, eventually we'll soon see that more drivers, maybe even kernel modules, could be completely replaced with eBPF, allowing the kernel itself to shrink in size, which is great because less lines of code to worry about, less security vulnerabilities to worry about, and we can have large pieces of the kernel implemented in safe, restricted C, and have the guardrails of memory safety there, which will hopefully help avoid a whole lot of bugs. Now, today, there are a bunch of program types and hook points and trace points that you can use for developing a eBPF and extending the kernel, and really they can be represented in this Venn diagram. So we have networking, we have security, and we have observability as being the three core use cases for BPF. We can change the way the networking stack operates, we can implement security operations, but we can also observe what is happening in the kernel in real time. Now, the intersection of these use cases become incredibly interesting. So when networking and observability intersect, we can look at the way the application is using the network with its system calls, but we can also look at the network traffic which comes on the wire as a result of that. Similarly, for observability and security, we can look at what an application is doing at runtime, and if we see it performing something anomalous, we could actually block that interaction with the kernel using the security subsystem. Equally with networking and security, we can look at traffic on the wire, and then we can perform a security operation in result of that. And ultimately, when you include all of these things together, we could actually develop a form of intelligent application sandboxing, where we can understand what the steady state of an application is, and we can take action to ensure that it doesn't escape the boundaries that we want to establish as its steady state. So the promise of eBPF is unbounded. There are so many different ways that we can compare and contrast and mix all of these hooks together that, you know, there are a lot of interesting ways that we can compose this together. So you might be wondering how it's already in use today. Now, at Red Hat, we obviously have RHEL, and RHEL is a very good base for eBPF. RHEL 9 has a very recent kernel version. It already ships with tools like SystemTap, Performance Copilot, XDP tools, BPF Trace. These are all observability tools available on RHEL today that allow you to leverage BPF for observability. In the intersection of observability and networking, we've got the Red Hat Network Observability Operator, which can be run on top of Kubernetes to give you some insight into the network traffic in your OpenShift cluster. And similarly, on the security side, we've got Red Hat ACS for Kubernetes, which allows you to understand the applications that are running on your systems and what they are doing from a security standpoint. So you'll notice that there is this sort of gap in the networking section where we're still trying to figure out where we can best leverage that for ourselves and for our customers as well. So why is eBPF particularly good for networking? There is a technology which is part of the BPF family called Express Data Path, XDP. Now, when a packet comes into a Linux device, directly off the network adapter, it will typically go through the networking stack. So we'll allocate some memory, we'll do a lot of processing to figure out is it a TCP packet, an IP packet, we'll do some filtering. There is a lot of processing that goes into actually dealing with packets coming off of the network card. Now, what XDP allows us to do is it allows us to grab this packet immediately after it's come from the NIC and perform some actions on it. Now, why this is incredibly important is for certain cases like distributed denial of service mitigation, or for firewalling, or for cases where a packet is coming in and we know that it needs to come directly back out again because we're performing some sort of load balancing. We can do that without stressing the host CPU as much because we don't need to run through that networking stack. So effectively, it gives us a shortcut mechanism for these type of behaviors, which allows us to get better performance and to protect that host CPU so more CPU time can be spent on applications and not trying to deal with network problems. Now, there are a whole bunch of other hooks within the networking stack that allow us to have programmability. We can program at the traffic control layer. We can control traffic at the C group layer. We can even control traffic at the socket layer, and even for making syscalls, we can start looking at which syscalls are happening from a network side. So we have this huge amount of programmability available to us in networking, which we can start thinking about building some very interesting tooling. But eBPF doesn't come without its challenges. eBPF development is hard, and it is really a mindset shift from traditional systems programming or even kernel development. It's very, very close to the Linux kernel, and it requires you to understand where exactly your program is going to be executed, how it's going to be executed, and to bear that in mind when you're writing it. Not only that, eBPF has moved very quickly. It was introduced in, I think, about 2014, 2015, and we have seen continuous innovation year on year on year, even up until this year, where we have new subsystems adopting BPF, new map types, new things to keep up with. And best current practice has moved very quickly over those years as eBPF has developed as a technology. One of the biggest problems with kernel modules were they were very much tied to a specific version of the kernel. So we had to keep rebuilding them every time the kernel changed. And eBPF has come up with a solution to that with a technology called compile once, run everywhere, which allows us to build our application once, and we can adapt it to the kernel that's running at load time. So if something has changed in the layout of a structure from one version of the kernel to another, we can actually account for that when we are loading our programming. But sometimes there are implementation detail changes that vary from kernel to kernel as eBPF has evolved, which are also hard to keep up with. But more so, one of the bigger problems facing us is that there isn't really an easy packaging or deployment solution for BPF programs. Not only that, but while we see the promise of BPF, a lot of other people, customers, partners, also see the promise of BPF. And if, as I predicted, more and more of the kernel starts to expose itself by BPF, we're heading towards this situation where everybody wants to use BPF, but there is no coordination on the system that allows multiple applications to coexist in certain places. And XDP is, in fact, one of these examples where it is exclusive. So the first program that gets loaded takes control of that network device, and no other programs can be loaded, which doesn't really strike us as a great experience. So how do we intend to solve these problems? Well, we're working with the eBPF Foundation, of which Red Hat are a member, to make eBPF easier to understand and to improve the documentation situation so we can help ease developers into eBPF and make that onboarding experience easier. Believe it or not, getting just a development environment set up for BPF is a non-trivial matter. So really, if we can solve some of this via documentation, we feel like we'll be able to bring more people into the eBPF space, and we'll be able to innovate at a faster pace. We're also investing in projects that improve developer experience. So myself as a Rust developer, I am contributing to a project called Aya, and Aya is a library which aims to try and solve some of these developer productivity issues. So Rust as a language has been voted, I think, top most loved programming language for the last 7 years in a row. So the developer tooling in Rust is absolutely first class. So we're trying to take that tooling and make sure that it's applicable in the eBPF space as well. Alongside that, we recognize the need for having better tooling for system administrators to manage eBPF on their systems. Sysadmins need to have control over who is loading what programs and which attachment points in the system. We also need to solve for cooperation and coexistence to allow Red Hat and for our customers and partners to be able to provide BPF programs and for us all to happily coexist on the same system. And at the same time, we want to follow that focus on supply chain security and making sure that if we are building BPF and our customers are building BPF and we're loading this into our systems, that we have some form of attestation. We can figure out that, yes, it was Red Hat who built this, or yes, it was my build system who built this, and make sure that we are loading signed programs into the kernel, because of course, you wouldn't want to load untrusted code into your Linux kernel. So I'm going to give you a short demo on how we're doing this, and it's going to be through means of an example. So let's say I'm a developer working at a corporation, and one of the problems that we've been having is we tend to get a distributed denial of the service attack every now and again, and we want the ability to be able to stop that in its tracks as quickly as possible. Now, I know that I could use XDP for doing this. I read it on the internet. Sounds like a really good idea. I want to try and get this done as quickly as possible because there is a pressing deadline. I'm not sure when one of these attacks is going to happen again. So what I'm going to do is I'm going to head over to my development machine. I'm going to scaffold a new project using a tool called Cargo Generate, which is part of the Rust tool chain. And I'm going to call it Red Hat Next. All right, it's an XDP program. Yeah, that's what I wanted to do. Cool. So what this has done is it's scaffolded me out a project. It's created a whole lot of best practices in there for how to build the project, how to code the project. It allows me to share code and structures between kernel space and user space. It allows me to build my Rust code into BPF, and it allows me to compile a user space application so I can run this and test it out. So then comes the development of the application itself. Now, I'm not going to go through all of the code that's here, but suffice it to say, developing networking applications is fairly not too difficult. Ultimately, if you've ever done a computer science course and you've had a class on networking, you're always going to have seen the diagrams that show you here's an Ethernet header and a whole bunch of fields in it, and then that's followed by an IP header with a whole bunch of fields in it, which is then followed by a TCP header or a UDP header with a whole bunch of fields in it. And effectively, all we're going to do here is just walk through that packet. So, does it have an IP header? Okay, great. I'm going to go and look at what's in that IP header. Is it TCP? Great, that's what I was looking for. Now, is the destination port 8888? Because I know that that's where I'm getting a whole bunch of traffic coming in, is on that port 8888. If it is, I want to drop that immediately. And if it's not, then that's fine. Like, that traffic can come through into my server. Now, I will also just highlight that one of the great things about using the Rust tooling here is it actually helps me from making stupid mistakes while developing. So it is going to nag at me continuously if I am doing something wrong, which is great, because if it's doing it now, it's not after I've compiled it and then shipped it off somewhere and then tried to run it and then I've found that out later. So if I were to do something really silly, like take this XDP thing and I'm going to make it a trace point because why not? And then I were to save that off. The Rust toolchain is going to look at this and it's going to say, ha, no, Dave, no. This is not a trace point. You're not allowed to call this a trace point because you've told me that you're putting in an XDP context here, but no, it's actually supposed to be a trace point. So having this tooling here in my IDE is able to make me a more effective BPF developer than if I were writing this in C, and there are absolutely no guardrails. It assumes that I know what I'm doing, which, to be honest, I don't. So anyway, I've written this program now, and I want to try it out. So I'm just going to do a quick cargo run, which is not going to be as quick, unfortunately. I assumed it had pre-compiled, but obviously I've changed something and now it wants to compile the whole thing again. So just bear with me while my underpowered machine tries to compile this code. All right, we're almost there. Well, it is now 3 years old, so it's starting to feel the strain of BPF development. Shoot, yeah, ask me questions if you want while we're waiting. It's no big deal. That's a good one.
Because people online can't hear you. So, I guess that a couple. The first time I can remember was a lot of the stuff he talked about as benefits sounded kind of like the same benefits you get from like doing unikernels. And I wondered if you had any insights into like things you could do, like bypassing, stacks and stuff like that.
Yeah, so I mean, unikernels in general are quite different. So the idea with a unikernel is that instead of having the Linux kernel that gives you absolutely everything, you would instead have some sort of library operating system where you say, all right, I'm doing storage, so I need a file system. I need networking, so I'm going to have a network stack. That could be your network stack. It could be a network stack somebody else has provided, but that's up to you. If it's your network stack, then yeah, sure, go ahead. Write it any which way you want. The nice thing about BPF is that we're still within the confines of the Linux kernel, and that we can just extend those behaviors generically for any user of the kernel. We don't require you to build your application with just the bits of the kernel you need. So solving a slightly different problem. eBPF is the more generic solution.
Yeah, I was curious. How do you test it afterwards once it's finished building? Do you usually go through a VM or what?
Yeah, so I've actually got so this is just on a VM. I tend to develop on a VM to try and keep my host system nice and clean. So at the moment, this is running. You can't see because there's no output, but if I were to open up a shell, so I've got a shell here, and I were to try to get hold of my dev machine on port 8000 where I've got a web server running, you can see that that's absolutely fine. If I try and get to a port that's got nothing listening to it, like 1234, what's going to happen is that the network stack is going to send back a TCP RST or an ICMP message to say, look, nothing here, right? There's nothing listening on this port. Because now I've got my application running and it should be blocking things on port 8888, if I run that, you're going to see that nothing's going to happen. It's completely uneventful because on the Linux side, we're intercepting that and just dropping it straight away. It doesn't touch the network stack. No TCP message or ICMP message comes back. Exactly. Which is great for DDoS. Like, why bother? Why would I need to do extra processing to go and shut that down when I can just, throw it in the bin and just carry on with genuine traffic? So yeah, I do a lot of development on VMs for this reason, just in case I shut myself out.
Well, thank you.
You're welcome. All right, so I've done my development here. I've proved that it's working in development, which is great, but that's only going to solve the problem on my laptop. The next problem I have is, how do I take this into production? So we do have a solution for that as well. So you remember that if you were at Jim's talk, he showed you that you could package WASM into a Docker container or a Podman container. Well, we can do the same thing with eBPF. So we can take the bytecode that we've written, we can package that inside a container, which gives us now a distribution mechanism. So we can push this up to Quay. I've got a little script here. Where are we? It's called build, sign, and push. So I do a Podman build, provide it some arguments just to tell it a little bit of metadata about my program. I'll then go and push that off to Quay. I can then sign it with my key. So I can say, look, I'm Dave, the developer. I have absolutely created this repository. It's totally fine. And I'm now in a position where I could run this on a production server. So I'm going to zip on off over to my production server. Now, this production server, I hadn't realized that somebody had got here before me, and they're actually using XDP for another purpose on the system. So I've been developing a tool called BPFD, and if I were to run BPFD list, hang on, let's reset this a second. if I were to run BPF cuttle list ETH0, I can see that there is already a program here running. It's got a priority of 50, and it's just a very simple program that's just passing traffic. But you could imagine for a moment that maybe somebody was running a tool here to gather packets for further analysis. Maybe it's they're passing packets into user space for me to look at later. Maybe it's an observability tool. Maybe I just don't know what it is, but I'm not allowed to touch it. Either way, I need to find a way of running my thing while cooperating with what's already here. Before I run it, I should be able to verify that I have put a signature on my BPF bytecode. So this uses cosign, which is part of the SigStore project, which our security team have been working on. So if I run cosign verify, I can verify here that yes, there is a signature on this, and hopefully at some point I'll be able to teach BPFD to be smart enough to actually skip this step rather than me manually verifying. It should be able to do this automatically. So if I were to run BPF cuttle again, but this time I'm going to load, I just need to provide it some metadata. So I'm going to tell it I'm attaching to the ETH0 interface, and I've got a priority of 10, which is lower than 50. So that means I want this attached ahead of the program that's running there. It's doing some DDoS prevention, so let's assume that that's safe. I should then just be able to hit enter. I get myself back a UUID. Great. If I list this out, I can see then that my XDP program has actually been attached ahead of the other one, sharing that same interface. And now if I were to perform the same test that I did earlier, but on my production machine this time, so curl over to prod, 888, you'll see same result again. So the traffic is being processed by XDP and being dropped immediately rather than going through the network stack. But if an unused port on that production server is going to fail in the same way that it would do in my development environment. So in summary, what I've been able to do here is using BPFD, I've been able to build out a program in Rust, scaffold it, quickly develop it, test it on my local machine, build it into a container, sign it, and then pull that container from my production machine and run that XDP program very similar to how I would do with like a Docker container on my production environment, while also sharing with other XDP programs that could already be loaded on that system. So that's kind of hit some of these challenges that we were facing, and hopefully if we can continue to develop this further and hopefully build some more community around it, that this will be something which we can start looking at shipping on RHEL to address this use case. Also, not as part of the demo, because I ran out of time, but one of the things that we have been looking at is building out an operator for this on OpenShift. So instead of manually deploying your XDP program to an individual node, you can write a Kubernetes YAML, deploy that into Kubernetes, and have that distributed to all nodes in the cluster. So yes, I'll pause now for any questions, either from the audience or online.
Can you mention a little bit about how a user space program would interact with this through memory maps? Or I don't think we've heard much about that, but I've heard a lot about memory map usage, and I haven't heard much said about that. So I was just wondering if you could explain how that's going to work.
Yeah, absolutely. So one of the slightly scarier aspects of BPF is there are a whole bunch of Linux capabilities that allow your program to do lots and lots of BPF operations. Some of the scarier ones are relating to loading programs that can trace running programs on the system, or to load an XDP program, you need capnetadmin, which doesn't just let you load an XDP program, it lets you manipulate any network device on the system. So by having something like BPFD do that, we reduce the amount of privileges that a user is going to need. A user space program is only ever going to need to read data that's been put into one of these BPF maps, and we provide a safe interface for them to do that from the file system. So there is a file descriptor pinned onto a file system somewhere. They can use BPF APIs with a cat BPF privilege, which will allow them to then read data in from that map or write data into that map to program the BPF program or to read data that is written to it. So in doing so, we hopefully reduce the security risk of running BPF in your infrastructure.
Thank you.
So you showed like the scenario where somebody else is already using a slot, and you're saying, okay, well, I'd like to load my code in there.
Yep.
What's the current state of like reasoning about interactions between those? I mean, can one higher priority thing like try to, you know, if it was malicious or unlucky or whatever, like kneecap what comes after it?
Yeah, I mean, absolutely. There's not a very clean mechanism for being able to express what a program can or can't do in the BPF world. So we're assuming that programs are going to be relatively well behaved, and we've got development guidelines for people writing programs to help them make sure that they can be well behaved in this environment where they're being chained. But yeah, absolutely. I mean, you could end up dropping packets in one program, which the other program might have really wanted to see. Ultimately, it would be nice to do this by machine, but we think that for now, having a system administrator, a human that understands the way that these programs are supposed to interact and can reason about the ordering is probably the best solution for now. So we want to provide that to users of BPFD to say, okay, the administrator knows best. He knows that this program is really important, this one not so much. This one needs to happen, packet filtering needs to happen before we do routing, etc. So,
Going back to Eric's question or comment on the unikernel, it makes sense from a performance perspective to move application logic into the kernel just to avoid domain crossings, maybe implement custom management of page tables or something along those lines. And if a library operating system existed that you could link against an application and turn it into a eBPF module, that seems like it would be a pretty cool and attractive thing. But from my understanding, the eBPF execution model is far more restricted than what a process is.
Yes.
So I'd like to hear you react to that thought of a library operating system, eBPF, and also just what, or maybe just moving general application logic into the kernel through eBPF. Is it a good idea? What would that application not be able to do? Like where would it just hit an absolute brick wall?
yeah, so there's a few constraints about the eBPF runtime which are super relevant. So one, it is stack constrained. It has 512 bytes of stack, which is not going to be enough for an application. It's barely enough for reading a file name from something, because file names can be way more than 512 bytes. So it's not a very good environment for applications. Aside from that, we're limited to 1 million instructions. So again, anything general purpose, which is beyond 1 million instructions, isn't going to be loadable right now. Aside from that, there is a whole lot of code gymnastics that needs to be done to keep the eBPF verifier happy. So ensuring that you make sure that your loops are bounded, ensuring that you check that things absolutely 100% can't be null in every branch of code that you've got in your application. So I really think that while it's absolutely excellent for kernel functions and changing the way that the kernel behaves in certain cases, that it's definitely not that general purpose programming environment for bringing applications into.
Very good. Thank you.
All right, there is a survey. Please be sure to fill out the survey.
Yeah, so we have a QR code right here. You scan it and just give us a survey on that.
And to encourage you to fill out the survey quickly, there is a happy hour happening. And I believe we will be shepherded in the right direction once we leave the room.
Yeah, so you guys get out, you want to head out to kind of the hallway, the room in the